Section 3.4, Day 1, we're solving linear programming problems. Here's the essential question. How can I solve linear programming problems? Please write that down. Who uses this? Landscape architects can use linear programming to determine which plants to plant on a green roof. So, what the landscape architects do is they choose different types of plants depending on constraints. These three constraints: the price of the plant, the amount of water they require, and the amount of carbon dioxide they absorb. These are examples of constraints. And all of these linear programming problems are going to be made up of constraints. Linear programming is a method of finding a maximum or minimum value of a function that satisfies a given set of conditions called constraints. A constraint is one of the inequalities in a linear programming problem. The solution to the set of constraints can be graphed as a feasible region. So in section 3.3, when we were solving a system of linear inequalities, that's what we were doing. Remember, we would shade above the line, below the line. And where the shadings overlapped, that was our solution. I had you shaded in really dark. That is called a feasible region. The inequalities in 3.3 that we were graphing, they are called constraints. So over here, I wrote the solution, because we talked about a feasible region, which is a solution. The solution is the shaded area where the inequalities overlap. And we did that in 3.3. So a lot of this is really a review of 3.3, but it's much more involved because we are using word problems and we are creating the constraints and then graphing. So I said bring colored pencils to class. You can, but I have them in class. I wrote bring a ruler to class. You don't have to bring a ruler because I also have a bin of rulers. But if you want to have your own, we're going to be using those next week. All right. And the one thing I want to point out why we're using rulers is because for this section, it is critical that your lines are exact because we're going to be coming up with the corners or the vertices, which are going to be used to determine the max or min. So it's very, very important. We're in 3.3. It wasn't as important because we weren't finding the vertices. We were just shading the region. Example 1. Yum's Bakery bakes 2 breads, A and B. One batch of A uses 5 pounds of oats and 3 pounds of flour. One batch of B uses 2 pounds of oats and 3 pounds of flour. The company has 180 pounds of oats and 135 pounds of flour available. Write the constraints for the problem and graph the feasible region. So over here, I said X is bread A and Y refers to bread B. I also wrote that bread is equal to oats plus flour because that's important when we're coming up with the constraints. So right now, I'm going to be coming up with, I know ahead of time, 4 constraints. Will you know that? No, we'll have to practice and figure that out. But I'm going to give you an always right now on these word problems. The first 2 constraints you're always going to write down is this. X is greater than or equal to 0 and Y is greater than or equal to 0 because I cannot make negative bread. It doesn't make any sense. So I have to use those 2 as my initial constraints. Now my other constraints, I'm going to put all the oats together and then all the flour together because it says the company has 180 pounds of oats and 135 pounds of flour. That means we have that many, but we don't have any more than that. So the 180 is the maximum. That means the alligator is going to be eating the 180. So if I scroll down, I'm going to write these over here. I'm going to write it down here. I'm going to write this. write the 180 like I told you. And I said the alligator, I'm kind of working backwards. Alligator has to eat the 180. And on the 135, the alligator's eating the 135. This is the oats for both breads. And this is the flour for both breads. And it says it up here. 180 goes with oats, 135 goes with flour. So now let's put all the yellows. I highlighted it to show what was oats. Well, batch A, remember A goes with X and B goes with Y. Batch A uses 5 pounds of oats. B uses 2 pounds of oats. So therefore, when we write our inequality that goes with the oats, we're going to have 5x plus 2y is less than or equal to 180. 5 pounds of oats go with A. That's why it's 5x. 2 pounds of oats goes with B. That's why it's 2y. The same thing with flour. A uses 3 pounds of flour. B uses 3 pounds. So that constraint's going to be 3. Try that again. Is going to be 3x plus 3y is less than or equal to 135. Those are the 4 constraints that go with this word problem. That's going to be the hardest part because we have not done that yet in 3.3. Now I'm going to go to the next page, and what we're going to do is we're going to graph the feasible region. Now, you might be saying, well, this graph looks kind of weird. I'm not used to this because normally Miss Young gives me graph paper where the y-axis is in the middle, the x-axis is in the middle. The only reason I have it set up like this is to give me more space because of these 2 constraints. Because it's stating that x is greater than or equal to 0 and y is greater than or equal to 0, we're only going to be over here. We can't be over here because x isn't negative, and we can't be down there because y isn't negative. That is the only reason. So I'm about to teach you a new method here for graphing a feasible region. We, so far, have been putting lines in slope-intercept form, which is wonderful. But when the numbers are really large like this, it gets to be a little bit more difficult. So then in that case, what we're going to do is we are going to find the x-intercept and the y-intercept for each line, and then we're going to connect the dots, and we'll worry about shading when we're all done. All right, so let's do that. So I'm going to start with 5x plus 2y, and I'm just going to say that equals 180. I'm not going to worry about the inequality right now because I'm not shading. I'm just trying to find the x and y intercept. Well, to find an x-intercept, we have to set y equal to 0 and solve for x. So that's what I'm going to do. That should be 36. I'm going to grab my calculator just to make sure that I'm not making any mistakes here. Yep. Okay. So we found a point right now. I'm going to scroll down, and the point we found was 36, 0. That is the x-intercept. An x-intercept means there's an x value, but there is no y value because it's a point on the x-axis. So what we're doing right now is we're taking care of this line right there. So now let's find the y-intercept. We have to set now x equal to 0 and solve for y. So 5 times 0. So that's 2y equals 180 divided by 2. Y is equal to 90. So that's 0, 90. That is the y-intercept. That's the y-intercept because x is equal to 0, so it's a point on the y-axis. So what we're going to do is we're going to plot those 2 points right now. And I think how I'm going to count on this graph, I'm going to count up by 10. So we're going to call this, let's change my color for a minute. Let's go like this. We're going to have this be 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And then going up this way, the same thing. We're going to have 10, 20, this is 30, 40, 50. That's 40 right there. That's 30, 60, 70, 80, 90, and 100. I'm just counting up by tens because otherwise my graph will go on forever. All right, so 36, 0, that's going to be about, this would be 35. That's going to be about right there. So I'm going to label that. That point right there is the point 36, 0. 0, 90, well, there's 90. It's going to be right there. So that is the point 0, 90. Okay. So now what I can do is I'm going to get out, you would have a ruler here, and I'm going to connect. There we go. So there, we connected those points. All right, next, we're going to go to the other line, which is the red line right there. I'm going to scroll down. We have 3x plus 3y equals 135. And again, we're going to find the x-intercept of this line. We're going to set y equal to 0. So we have 135 divided by 3 is 45. Okay, so we created the point 45, 0. What we found was the x-intercept. All right, on the other line, the same line, which is right there. Now we're going to find the y-intercept. And notice, when we're finding the x-intercept, that's a point on the x-axis, y is always 0. When we're finding the y-intercept, that is a point on the y-axis, we're setting x equal to 0. And you can always use this method over putting your line in slope-intercept form. We already did that. That's 45. If you prefer to find the x and y intercepts, you can do that. That's why I'm showing you this other method. For this problem, that's really the only way to do it. But when it's other problems where you can put it in slope-intercept form or use this, you can choose. All right, that's the y-intercept. So let's graph those. 45, 0 would be about right there. 0, 45 would be about right there. I'm going to draw a little line. That is 45, 0. And I'm going to draw the line. That is 0, 45. Grab out my ruler. And there we go. Perfect. Okay. So now what we have to do is we have to determine, where do we shade? Here's the problem. When the lines are in slope-intercept form, meaning y equals mx plus b, we can look at just the inequality, or we can use the test point, decide shade above or below. Right now, neither of these lines are in slope-intercept form, so we cannot say, oh, for the blue line, it's less than or equal to shade below. You can't do that. So the only way to do this, and what I'm going to do, I would just want to make sure that we are very clear of something. I want to make sure that we know that this is our blue line. I think it's clear because of the points. And this is our red line. Okay. So when it's not in slope-intercept form, then we have no other option but to use a test point to determine where we're shading. So obviously the test point that I'm going to use is 0, 0, which is right there. So my test point is 0, 0. Let's plug it into the blue. We have 5 times 0 plus 2 times 0. Is that less than or equal to 180? Is 0 less than or equal to 180? Yes, it is. Yes. So for the blue line, I am definitely going to shade this way. Okay. So let's grab out my highlighter and let's do that. I'm not going down below because x has to be greater than or equal to 0. So we have to stay right here because of these. We can't shade that way. We can't shade below because it states that x is greater than or equal to 0 and y is greater than or equal to 0. So now the red line, again, we're going to use 0, 0 to test. So that's 3 times 0 plus 3 times 0. Is 0 less than or equal to 135? Yes. So for the red line, we also have to shade below. So there we go. And like I've done in class, where the yellow and the blue overlap, it turns to green. And then that is the solution. So the green is it. So now this part we've already done, but here's the part that we haven't done. We have to find the vertices of the feasible region. So what that means is the vertices of the feasible region. Well, number one, there are 4 different constraints, meaning there are 4 different sides to our region. So we're going to go like this, and we're going to outline that. So we have 1, 2, 3, and 4. Right there. Okay. So we have to find right now, and I'm going to do this, we have to find that point, which we know, that point, we have to find that point, and we have to find that point. The corners of our feasible region are our vertices. Students always ask, how do I know? Sometimes it's difficult to tell. I think of it like this. I start at one of the vertices. Let's start here. And I say, okay, I start driving and I have to turn to remain in the green feasible region. Vertice. Okay, I drive and I have to stop and turn because I have to stay in the green. If I keep going, I'm going to go to the yellow. That's another vertice. And I keep driving and I have to stop because if I keep going, I won't be in the feasible region anymore. And that would be the, that would be the 4th point. And here's the deal. We already know that this point, it's labeled, is 0, 45. We already know this point right here, that's 0, 0. We know this point right here, we labeled it, that's 36, 0. So we can write those down right now below. So find the vertices. So I'm going to write vertices and we'll label it. So we have 0, 0, 0, 45, and 36, 0. Those are the three we know. The only one we don't know is this one right here. And how we find that one out is, look, it is the intersection of the red line and the blue line. So what we will have to do is use what we know about solving. Really, in this case, we're solving when we solved systems of equations, we look to see where the lines intersected. They intersect right here. When two lines intersect, we can find out what x value, what y value do they have in common, and that will be our final vertice. What we're going to do, because I don't want to make this video so long, is we're going to finish that in class and show you how to find that fourth vertice. We're also going to talk about this in class and finish the Yum's Bakery problem. And then we have another example to do. And then right here are your video questions. Please answer them in your notes.